goes to events. Here we go. Okay. Here is an elevation versus time graph of a person's motion. Can we describe what the person might have been doing? So let's look at this graph. So we've got elevation going on. We've got time. What do you think this person's doing? Climbing a mountain. That's correct. I would agree with that. Okay. So, I almost lost the top to my pencil. Oh. All right. All right. So here we go. Let's describe this. And I'm going to start a little bit up here. 1. Okay. What is the first section would be this part, and I would take it like this and probably come down, and just so we can see what's happening. So that's from when they start to here. What do you think they're doing? What kind of motion? You think they're walking? Well, they're hiking for sure, right? If they're going up a mountain, we'll call it hiking. So we're going to do the time, which is 0 to, what do you think this is? 3. So from 0 to 3 minutes, a hiker climbs up a hill at a, what kind of rate do you have if you have a line like this? What do we call that kind of rate?
You said undefined.
Undefined is an up and down slope. What do you think? It looks pretty, what's that C word?
Negative.
Constant. Okay? It's pretty constant, right? It's not changing. It's not curving. So at a constant rate until, do you want it to be a guy or a girl? A guy. Okay. Until he reaches what height? Where did he reach? 10 feet. Okay? So then let's take the next section of the graph, which would be from here to here, in my opinion. Okay? And I hope in your opinion. Do you agree with me? All right. So that is for approximately how much time? 1 minute. So what do you think happens at this point? He takes a break. Good. So he rests or takes a break for about 1 minute. Okay. So then we want to talk about the next section, which is here. What do you think happens there? My line's probably a little too close to 4, but he's like going steep, isn't he? For about how long? I would agree. So he climbs 5 more feet in about 30 seconds. Because he got to this elevation, which is 15, isn't it? Okay. So when you have an elevation versus time, you want to talk about where your elevation is and how long a period of time that is when you are describing the different parts of the graph. All right, so we've got number 4, which lasts from here to about here. And let's see. So do we climb any more in elevation? No. He's probably resting. And for how long is he resting? Okay. So hiker rests for about 1.5 minutes.
Is it Halloween this week?
What?
Is it Halloween this week?
No, next week. So, what do you think happens from here to here?
He starts climbing down.
I'm guessing he either falls or he runs down that hill, doesn't he? Because he took 4, 5, almost 5 minutes to get to here, but look at how quickly does he come down?
30 seconds.
No, probably a minute. Okay, so he's really done a number coming down. He's going pretty fast, isn't he? So let's say hiker falls, runs down the hill.
I've been on fishing
For about 1 minute. And I'll tell you why I think he fell in a second here after we looked at this next one. What happens between here and here? Nothing. So what is he doing?
Making sure he has rope roots.
There you go. He's resting, right? If you fell down a hill, you'd be stopping for a couple of minutes anyways, right?
Or he's dead.
Or he's dead. But then, see, he continues over here. So,
Yeah, I was gonna say something drastic.
I think he skied down the mountain and just stopped to take off his skis for that long.
there you go. So here he took one lift to here. Then he had to walk over to the next ski lift and took another lift up here, huh? That's good. And then he had to walk over here to the edge of the slopes. So then he went down the slopes. And then there kind of was like a little spot where he had to kind of ski through and then went down the bunny hill. Is that what you're trying to say? Ah, true snow skier. Okay, so let's just say he rests for about, since we haven't used the skiing analogy, otherwise we would continue with that, for about a minute, right? About 1 minute, a minute. What happens, the last thing that happens?
He stops.
Well, from here to here, what is he doing?
Oh, going down.
He walks the rest of the way down the hill for about how long? 2 minutes. And like you said, that would make perfect sense to me. The ski lodge, the skiing scenario. Okay, so there's not just one answer to this, but you have to get the going up and the acceleration and the time and that kind of thing. You could make this to be different things. Going upstairs, going into a different building, going upstairs again, getting to the roof, taking a nice look, falling off roof. Okay? Or what we could do? We could do those. Well, no, because that would be straight down. Do it. If you kind of do that rock climbing thing where you propel down, that would be straight down, not to the side. All right. It says, what was the average rate of change of the person's elevation between time 0 minutes and time 4 minutes? So there is a formula that you guys probably are not familiar with. And I'm going to write something up here and then we'll manipulate it. Distance equals rate times time. Okay? Do you know that formula? You will, because you need to know that formula for science. Okay? It's probably on your science formula chart. So, we need rate, because what was the average rate is the question. So if I manipulate this formula, D equals R times T, how do I get R by itself? No, because this is multiplication. What do I do? What's the opposite? Divide by T on both sides. Those cancel out. I end up with D over T is equal to R. Okay? So since I need rate, I am going to use that formula. So I'm going to come down here and put R equals D over T. What is my distance that we're going between 0 and 4 minutes? If you look at your chart, how far did you go between 0 and 4 minutes? What is the distance? 10 feet. What is the time? 4 minutes. Of course, we need to simplify everything. So what do we get? 2.5 feet for 1 minute. And I wouldn't make you write that out of the sentence as long as you identified what 2.5 over 1 meant. Because this tells me it's 2.5 feet for 1 minute. Okay? Good?
I'm ready to play tennis today.
You're not going to play tennis today.
Well, there we are.
All right. This is just, you're not going to need to know this, but we'll tell you what it is. A real piecewise linear function is the union of a linear functions on a real number line of intervals. So that's kind of what we're doing. We're piecewising. We're putting together different linear functions within a graph. Okay? So this time we're going to have to graph our information. A swimmer climbs a ladder for 2 seconds to a water slide that is 5 feet high. She sits for 2 seconds at the top of the slide and then slides to 8 feet down the slide into the water in 2 seconds. She stayed steady at the same position underwater for 2 seconds before rising to the surface of the water in 1 second. She remained in the pool for 1 more second. So, we need to start at 0, 0 because she's going at the bottom of a ladder, right? And how far does she go? In how long? So I'm going to go over to 2 seconds because my time is on my X and my elevation is on my Y. So I'm going to go over to time and then I'm going to go up to 5. 1, 2, 3, 4, 5. And I'm going to connect those 2 points. Then what happens? She sits for how long? 2 seconds at the top of the slide. So I need to go over 2 and draw myself a picture of that. Then she what?
She went down in 2 seconds.
So I'm going to go over to 2, the 2 seconds, and then count down. 1, 2, 3, 4, 5, 6, 7, 8. And then connect that. What? It's kind of like connect the dots. Follow the instructions and connect the dots. There you go. Okay. All right. Then what happens once she hits the water?
She stays
Underwater for 2 seconds. So over to 2. She's going to stay in the same place underwater for 2 seconds. Okay. Then what happens?
she rides in 1 second.
She rises to the surface. Where is the surface?
Equal or nothing on it.
Zero. Well, at where y is equal to 0. And that, how long did that take? 1 second. Okay. And the last thing.
She remained in the pool for 1 second.
Okay. So she's inside the pool for 1 more second. Everybody good? Okay. What was the average rate of change for the swimmer going up the ladder? So I'm going to write both my formulas here so I know them in case I need to go to them. I know rate is what we need right now, so I'm going to put rate over distance over time. What was the average rate of change for the swimmer going up the ladder? Well, I got R equals D over T. So what is my distance? Going up the ladder is 5 feet. And what is my time? 2 how much? Seconds. So if I do 5 feet in 2 seconds, how many feet in 1 second? 2.5 feet in 1 second. Okay. What was the average rate of change for the swimmer as she went down the slide? So same formula, I'm using rate. So how far did she slide down the slide? 8 feet. No, it's not asking us, it's just asking us for the rate of change. You know what? But that's probably a good point I've never even thought of. That it would be a negative rate of change because she went down. Probably true. Mm-hmm. And how long? How long did it take her to slide down the slide? 2 seconds. So what is our rate of change for? Because see, she's okay, let's talk about whether this is negative or positive. Because she's going down the slide at an accelerated rate.
But if it was positive, she'd be going up.
Okay, I'll agree with you. Negative 4 feet over 1 second. Okay. I gotta put myself a big star there so that I catch that every time when I teach this now. Look what you did to me, Alberto. You fixed me. If you measured from the top of the girl's head instead, she's 5 feet tall, how would your graph change? So what is that? Well, how would the graph change? What is it when we slide something on a graph? What do we call that movement? Yes? Say it. Translation. Okay? Remember that from 8th grade? Reflections is flipping. Translations are sliding. Rotations are turning. Okay? What? So, some pieces of the graph would, pretty much all pieces, be translated. I'm trying to do this in mathematical language. And are we going horizontally or vertically? Vertically in a positive direction 5 feet. All right, we got 2 more examples, so I guess we should get going here. This one isn't bad. All right, I'm going to read this, and then I want you to choose which graph you would choose, and then we'll see where you're at. A car traveling at 23 miles an hour accelerates to 46 miles an hour in 5 seconds. So if I was doing this, I'd be going 23 to 46 in 5 seconds. Okay, just to get myself some notes. It's very difficult to try and work problems in the paragraph. All right. It maintains the speed for 5 seconds. So then it's just going to go flat for 5 seconds. So I really could even do this. It's going to go up here. It's going to go flat. Then slows to a stop in 5 seconds. Stops in 5. Which graph demonstrates the car's speed over time? So if it slows to a speed, I'm actually going to go down, aren't I? In 5. Which graph demonstrates a car's speed over time? I'm going to let you look at them. (23 to 46) in 5 seconds. Maintains that speed for 5 seconds. Then slows to a stop in 5 seconds.
It's C. Not C. Totally D.
How many of you chose C? C would be your correct answer. First off, you have to start at 23, so it can't be B and it can't be D. That wipes those out because you have a y-intercept at starting point of 23 miles per hour. Then it says it goes up to 46. Does this go to 46 right away? No, so it can't be that one. Okay. All right, one more example. Actually, 2 more, but. All right, the graph below shows your speed at different times riding a bicycle. Isn't that fun? For how long, this is easy stuff, for how long were you going uphill? Let somebody else answer, Alberto. For how long were you going uphill?
9 seconds. Wait, no. 3.
Everybody good with that? You're going uphill until 3 seconds. 3 minutes, actually.
Oh, yeah.
Okay? For how long were you going downhill?
You want to let somebody else answer?
Yeah. Somebody said it. Who said it? 4 minutes is correct because you can't say 7 because you had this part that you were going up. So it's only from 3 to 7 that you were going down. Okay? For how long were you riding on level pavement? 3 minutes. That was difficult, wasn't it? Very difficult, I know. All right, let's look at this thing below. We got speed and we got time, okay? The graph below shows the speed of we're going to put school bus on its daily route because most of you are not familiar with city buses. But city buses basically run just like a school bus. They have stops, they have a path, they have a route that they do, and they stop to drop off passengers and stop to pick up passengers. So it's just the same kind of thing. The graph below shows the speed of a city bus on its daily route. Explain each label section of the graph. So we've got from 0 to here for A. So what do you think is happening in that first part? So the bus starts out at what? 0 speed and 0 time, right? So bus accelerates from a stop. Everybody good with that? Okay, because it speeds up from a stop. B, what's happening here? Maintains its speed. Maintains speed for a period of time, huh? We don't know how long that is because we don't have intervals on our graphs. So then what happens here for until, okay,
It goes to a stop.
so for a period of time, then I guess you could call, I don't know, I guess they're saying this time for C is here. It's going to slow, correct? And stop
Speed up again.
for a time. And then what does it do? Yes. Bus accelerates again. And that's basically what happens on your buses, right? You go from one stop to the next, and then they pick up speed. They go on that speed for a little while, and then boom, you gotta stop and pick up some other kids or drop other kids off, right? Okay? And that's basically what this is. I do want to make a note while I'm on camera that if you're doing number 2, the process is you want which graph most likely represents each of the following. You need to read this and figure out which graph you think matches A and write that number out here. Then you're going to read B and figure out which graph represents B and write that number out here. Then you're going to read C and figure out which graph does that. Then you come down here and find the correct order for A, B, and C for the graph numbers. All right, that was that.